The topic is query processing. The basic steps in query processing are parsing and translation, optimization, and evaluation. First, we know that what is query processing. It refers to the range of activities involved in extracting data from a database. The activities include translation of queries in high level database language into expressions that can be used at the physical level of the file system, um, and a query optimizing transformations and evaluation of queries. The first step is parsing and translation. The first action the system must take in query processing is to translate a given query to its internal form. This translation process is similar to the work performed by the parser of a compiler. In generating the internal form of the query, the parser checks the syntax of the user's query and verifies the relation names appearing in the query, or the names of the relation in the database, and so on. The system constructs a parse tree representation of that query, which then translates into a relational algebra expression, which is a low level language. The input query in the form of SQL query, which is called as high level query language. Furthermore, the relational algebra representation of a query specifies only a partially how to evaluate a query, and we should consider the query. Here, select balance from account where balance is less than 2500. This query can be translated into either of the following relational algebra expressions. There are two relational algebra expressions. The first one is select balance is less than 2500 and project balance of account, and the equivalent another relational algebra expression is project balance and select balance is less than 2500 of account. To implementing the selection, we can search every tuple in account to find tuples with balance less than 2500. If a b plus tree index is available on the attribute balance, we can use the index instead to locate the tuples. To specify how to evaluate a query, we need to provide not only the relational algebra expression but also to we have to give instructions specifying how to evaluate each operation. A relational algebra operation annotated with instructions on how to evaluate, it is called as evaluation primitive. A sequence of primitive operations that can be used to evaluate a query is a query execution plan or query evaluation plan. Here the query evaluation plan for this example, for the balance is less than 2500. The query execution engine takes a query evaluation plan and executes the plan and returns the answer to that query. The different evaluation plans for a given query can have different cost. In this example, we have two different relational algebra expressions. Each evaluation, it is called as evaluation plans. Each evaluation plan for a given query can have different cost. Measures of query cost. The cost of query evaluation can be measured in terms of number of different resources, including disk access, CPU time to execute a query, and in a distributed system or parallel database system, and the cost of communication. The response time for a query evaluation plan, that is the time required to execute the plan, could be used as a good measure of the cost of the plan. In large database systems, the disk access are usually the most important cost, since disk accesses are slow compared to in-memory operations. Most of them consider the disk access cost as a reasonable measure of the cost of query evaluation plan. The number of block transfers from disk is also used as a measure of the actual cost. For more accurate measures, we should find out the number of seek operations performed, number of blocks read, number of blocks return, and then add up these numbers after multiplying them by the average seek time, average transfer time for reading a block, and average transfer time for writing a block, and respectively. For simplicity, we just use number of block transfer from disk as the cost measure, and also we ignore the difference in cost between the sequential and random IO for simplicity. Also, we ignore CPU cost for simplicity because it is more difficult to calculate. Um, Real systems take CPU cost into account and differentiate between the sequential and random IO, and also it will take the buffer size into the account. We do not include cost to writing output to disk in our cost formula. The selection operation, we should consider a selection operation on a relation whose tuples are stored together in one file, and two scan algorithms are used to implement the selection operations. The basic algorithm is A1 linear search. In a linear search, the system scans each file block and tests all records to see whether they satisfy the selection condition. For a selection on a key attribute, the system can terminate the scan if the required record is found without looking at the other records of the relation. And the cost of the linear search in terms of number of IO operations is denoted as BR, where BR denotes the number of blocks in the files, and the selection on key attributes have average cost of BR divided by 2, but still it have a worst case of BR. And the advantage of linear search algorithm can be applied to any file, but the disadvantage is it is very slower. And the next algorithm is A2 binary search algorithm. If the file is ordered on an attribute and the selection condition is an equality comparison on the attribute, we can use a binary search to locate records that satisfies the selection operation. The system performs the binary search on the block of the file, and it required and we have to find a block containing the records in log base 2 b, where b denotes the number of blocks in the file, and also the cost for reading the extra blocks has to be added to the cost estimation. And these selections using indices, search algorithms that use an index are referred to the index scan. Search algorithms that use an index are A3 primary index on candidate key and equality on key. For an equality comparison on a key attribute with a primary index, we can use the index to retrieve a single record that satisfies the corresponding equality condition. And A4, primary index equality on non-key. We can retrieve multiple records by using a primary key index when the selection condition specifies an equality comparison on a non-key attribute A. The cost of the operation is proportional to the height of the tree, plus the number of blocks containing records with the specified search key. A5, secondary index and equality. Selection specifying an equality condition can use a secondary index. This strategy can retrieve a single record if the equality condition is on a key. Multiple records may get retrieved if the indexing field is not a key. In the first case, only one record is retrieved and the cost is equal to the height of the tree plus one IO operation to fetch the record. But in the second case, each record may be resident on a different block, which may result in one IO operation per retrieved record. And A6 is the primary index and comparison. A primary ordered index can be used when the selection condition is a comparison. For comparison conditions of the form A is greater than V or A is greater than or equal to V, a primary index on A can be used to direct the retrieval of tuples. For comparisons of the form A less than V and A is less than or equal to V, index lookup is not required. We use simple file scan starting from the beginning of the file and continuing up to the first tuple with the attribute A equal to V. And A7 is the secondary index and comparison. We can use a secondary ordered index to guide retrieval for comparison conditions involving less than or equal to, greater than or equal to. And the lowest level index blocks are scanned either from the smallest value up to the V or from V up to the maximum value. And the complex selections are A8 is the conjunctive selection using one index. Here we use conjunction, disjunction, and negation. A8 is the conjunctive selection using one index, and A9 is the conjunctive selection using multiple key index or composite index. A10 is the conjunctive selection by intersection of identifiers. And A11 disjunctive selection by union of identifiers. So these are the algorithm for selection operation for searching and selecting using indices, and it involves comparisons and some complex selections. Thank you.